Okay, I might just get started with my introduction, just because it's going to be fairly short. It's really just introducing some of the many acronyms we have in this kind of community. But I want to make sure that our first speaker has plenty of time to get started. So okay, good morning. Thank you very much for coming. This is the second meeting of what's called a special interest group, and I'll explain SIGS and UK Fluids Network and all of these different acronyms. So this conference ended up being online, as most conferences have for the last couple of years, but James and Matthew have helped me organise this, and obviously it's easier to do it online compared to in person, but it has been a reasonable amount of work shortlisting and kind of chasing up people. So thank you very much to them for all their help, and they'll be chairing the sessions. Any problems at all today, please let them know, or me know, and we'll do what we can to kind of help out. In terms of admin for Teams and the actual technical side, I think only I have ownership, just because we created it at Brunel. So if it's something to do with that, you're best to email me. I'm aware by saying this to people already in the team, it's maybe not too relevant, but okay. So the plan for today, if you want to look at the conference proceedings, you have it here on the website. So I sent this last night, so you can click this link directly, or you can go to this. So we start with Peter and Billy, and then we move on to Zhang, and then we have a discussion session. Our second session goes till lunchtime. We have an hour for lunch. The idea with lunch is, again, people are free to talk on Teams. I think one nice thing is you can kind of call people directly, anyone you want to catch up with. But the other advantage of these is just feel free to kind of turn your video off and get a snack whenever you want. So there's no no problem with that, I think, which is why we've kind of kept it fairly packed. There's not break sessions as such, because you can break whenever. And then, for the afternoon session, we go to discussion at 2:30. And then the final discussion session is at 5:15, and that's a slightly shorter one. And then at the end, I'll present just a small kind of finishing discussion on the Ian Snook Prize, which I tried to get Bill Hoover to speak at this conference, and I don't think he really likes the kind of online conference, but he was keen for me to kind of present some bits and pieces on that, so I'll give that towards the end. So just a couple of quick notes on Teams. I mentioned this before, but if you're in this meeting, of course you managed to get in. Can I just double check? Someone let in the person who came in a second ago, right? You guys can let in people.
Yeah. I think we can all admit people.
That's great. Yeah, perfect. Okay, so good. Okay, so just a quick explanation of Teams terminology for anyone who hasn't used it too much. There's a team. Within the team, there are channels. These channels you can think of as kind of discussion threads. So normally in an organization, that would be different projects. Here, they're different rooms within the conference venue. And then the meetings occur within those. So this meeting is within a channel, which is within the team. Not my jargon, but the key point here is that if you want to be able to see the different channels, you have to be within the team. If you've gone and just directly clicked the link, so I've now put this on the website, but if you've just directly joined the meeting by clicking this link, either in the email or on the website, what you'll find is you can only see the current video chat. So you'll only be able to see the kind of discussion we're having now. You won't be able to see the kind of wider infrastructure of the team. So what you can do is you can change the top right hand corner. See if I'm confused now. Click here, and then you can change to Brunel University as a guest. If you do that, you then have access to the various parts of the team. You should be able to see all the discussions. You can also access other bits and pieces. So on here, there's the program and website you can view. So this is directly linked to the website. So it's kind of a browser within here. There's also files. We've got the conference proceedings uploaded actually within the general. Again, the files are within each thing. So I'll try to keep all the files within general. And then it also means that you can post messages. So, again, please put in thoughts, ideas. If you want to kind of create a meeting within this where you have a quick discussion, or someone wants to present in a discussion session, a 5-minute bit on their work, or any of that's possible within this. And if anyone wants more discussion rooms, we can very easily create new channels. So if you wanted a new discussion room just for you to have a chat with someone you wanted to catch up with, then that's obviously possible. You can also directly call people. So the idea is to try to make this as kind of informal and like a real conference as possible within the confines. So this is just some advice on how to do that. So if you can add channels, that's great. You should be able to, even as a guest, but if not, you can ask us, and then you can directly chat by calling people. You can create new meetings. And again, ideas for discussion sessions would be great. Questions for speakers are brilliant, and those questions for speakers could come after the talk and could be posted on the channel, and you could say, I was really interested in this talk, please answer this, and then it might be useful for everyone else. So in the same way you'd ask a question in a conference, typing it in after the event's not a bad idea. So please consider doing that. Any questions on that? Anyone got any burning Teams questions? Or a lot of people have used Zoom only, so anyway, hopefully it's not too bad. Okay, so the backup option is to go directly to the link. Hopefully everyone's in the team, and then just bear in mind, if you are in the meeting, you'll only see that meeting. Okay, fine. So quick introduction from me on basically the reason this non-equilibrium molecular dynamics special interest group exists. So the UK Fluids Network was a UK funded project that ended in 2016. Sorry, in 2020. It was funded in 2016, and the idea was really to kind of fund a group of a set of small communities to be built that weren't necessarily aligned with kind of mainstream fluid dynamics, the kind of big areas, and really target the sort of emerging areas to have the potential to create sort of step changes, as they say. So this is a bit old, this slide, but previously they supported about 40 special interest groups. If you go to the Fluids website, I think it's gone up considerably. The original deal was that you applied to do one of these special interest groups, and they gave you a small amount of money for conference, a couple of £1,000, and then the idea is you then fund your next conferences. Now the nice thing about doing this online is it doesn't cost us anything. So this one we've done free, but in the future, if anyone would like to host or has a bit of funding for a conference, then we can definitely advertise it through this. We can do it under the banner of this. It's meant to be a UK based consortium, but to be honest, it's really just I think historical, and we can definitely grow something more international from that. It's my opinion. So a special interest group, as I mentioned, is this idea of separate areas within fluid dynamics which we target. Now, the logic of doing a special interest group in non-equilibrium molecular dynamics was really to target this kind of, I would say, gap between statistical physics and doing fluid dynamics with molecules. So we already had a really good SIG in fluid dynamics across the scales that definitely covered molecular dynamics, but also extended to sort of lattice Boltzmann and lattice gas. The idea here was to do something that's kind of more focused on the NEMD type of problems. So there's that's the division. You can tell I'm out of practice with this, struggling with all the tabs. Okay, so the other acronym is NEMD. I'm hoping everyone here at least knows what that means if they've come to this meeting. But it's essentially, the key point is you're modeling discrete molecules in continuous space. So for me, that's the kind of key distinction. Rather than a kind of continuum approach, you're doing the kind of individual molecules, and you're actually explicitly modeling their time evolution, as opposed to kind of statistical methods like something like Monte Carlo or kind of mean field approaches like lattice Boltzmann or fluid dynamics. And so part of that is having the interaction between the particles from intermolecular potentials. So that for me is the kind of distinction for the molecular dynamics. And then what you see from those molecules bouncing around is this kind of emergent property of the fluid dynamics. So, you get all sorts of nice behaviors that are, uniquely molecular. So the stick slip near walls, the liquid structure coming from the viscosity itself. And then, this overall behavior of the fluid, in this case, is kind of colored by velocity, where it's kind of positive and negative. You can actually extract fluid dynamics from the movement of the molecules. And you get, something like Couette flow from that. So this is kind of one aspect, is, just running some molecular simulation and averaging it. I would say the other thing that, really we bring as a community, and this is where the link to fluid dynamics and the UK Fluids Network is important, is we have this whole, physics, chemistry community where all of these concepts of radial distribution functions, liquid structure, fluctuation theorem, Liouville's equation, and then the way we actually get viscosity and surface tension from the underlying system. And these are just some examples. This, I think, is where we have kind of real ability to offer to the fluids community in kind of understanding how we can actually get these kind of emergent properties and linking, the statistical mechanics to the fluids. So that was the real kind of incentive for doing that. So the subject and scope is NEMD is fundamental fluid dynamics, but using MD. And the non-equilibrium here is because of the origins in thermodynamic, and you've got things like wall motion, temperature or pressure gradients driving a fluid away from thermodynamic equilibrium, or you have a kind of equilibrium with an interface. Locally, it's kind of spatially inhomogeneous. And this is fluid dynamics. All of these problems are exactly what we're studying in fluid dynamics. But we can simulate these problems in a more fundamental way. And we can also, that should be statistical mechanics underpinning, but we have this theoretical underpinning that we can essentially make sense of fluids problems. And I would say there's a massive growth recently in people using molecules to simulate things. And essentially, I think what we have here is a community of people with expertise in kind of the fundamentals, and this is really where we can add value. So last thing to say for me is just please sign up to the UK Fluids Network for any future announcements. Again, this should be UK based, but I think anyone internationally, if you sign up, there's no problem at all. If you're interested in any future meetings, and obviously if we have an event, we probably can't fund international attendees, but if you're willing to come, then obviously we'd love to have you. So yeah, I think it's pretty much what I said. Just basically expose the UK Fluids Network to the benefits of NEMD. And from this we can gain new perspective on important fluids problems, and then links to problems of interest to industry. The last thing to say for me, it's just on the discussion sessions today. So we've got discussion at 10 to 10:30, 12 to 1, 2:30 to 3, and at 5:15 to 5:40. We had a couple of suggestions for discussion sessions. I'll put them into the discussion sessions as notes, but questions like these are great. So, does the atomic description really affect the macroscopic properties such as contact angle, surface tension, or friction, or are these effects kind of essentially irrelevant? And is it worth trying to couple scales? Is the multi-scale modelling thing just a load of nonsense? Can we establish, the kind of blue skies in NEMD as a funding area? And the usual question of how we link to industry. So that's it for me. I think now we're at 1:30, so I don't want to take any of Peter's time. So unless there's any urgent questions or anyone any concerns, then I'll hand over to Peter for his talk.
Okay, so thank you very much, Ed, for organising the conference and also giving me the opportunity to speak here. And looking at the program, it looks amazing. I wish we had events like this in Australia. But it's fantastic to be able to join you, and maybe this is an unintended benefit of having so many conferences online now, is that we can join you quite easily for something like this. So the thing I'll be talking about today is energy and temperature in NEMD simulations, and in particular in relation to thermostating, and maybe looking at a conceptual problem with entropy production. So why do we want to use non-equilibrium molecular dynamics methods? Well, probably the main reason is for efficient computation of transport coefficients. That's where NEMD really shines. It's excellent for that. But we can also study nonlinear response. So, for example, in the fluid dynamics area, that would include normal stress differences. And we can also study the non-equilibrium steady state response, and including things like structure, ordering, phase transitions induced by flow, and all sorts of different things can be studied by non-equilibrium MD methods. And then why should we restrict ourselves in some cases to homogeneous non-equilibrium MD methods? Well, the benefit of that is that you get your simulation occurring at a single well-defined state point. And what that means is that the properties that you compute will be specifically defined at that state point. So you don't have a range of temperatures or a range of densities. And if you eliminate the boundaries with periodic boundary conditions, then you can use the whole system because it's all at the same state point. So it's very efficient because you're using all of the particles to calculate your properties, not just the ones in the center where the properties are uniform. And you have well-defined driving forces, which means that you can apply response theory, which is not always the case with boundary-driven methods. Now, having said that, there is a place for inhomogeneous methods, definitely. So we're talking about boundary or reservoir-driven methods. For example, in the figures below, we can imagine sliding plates, so we can have walls that are sliding relative to each other, producing shear flow, or we could apply a sinusoidal force to the system and get periodic perturbations. And I think both of those methods can implemented in some of the major MD packages, so they're definitely available to you. I guess one of the advantages of inhomogeneous methods is that you do avoid the homogeneous thermostats, which can sometimes be problematic. So there are pros and cons to both homogeneous and non-homogeneous NEMD methods, and you really need to choose the methods that's appropriate for the system that you want to look at. So let's look at a boundary-driven shear system where we have a couple of walls and they're moving relative to each other, and we have a fluid in between. And in that case, the heat that's produced by the shear, the dissipation due to shear, that's removed by conduction to the walls in this particular type of simulation. So we can thermostat the walls and remove the heat naturally, and that means that there's no sort of artificial thermostat applied to the fluid. So in that case, we have temperature, velocity and heat flux profiles that we can look at. The temperature profile is quadratic, the velocity profile is linear, and our velocity gradient is essentially constant except for a few wiggles near the walls where we have quite a strongly varying density due to the packing of molecules at the walls. And the thing I want to bring your attention to is the fact that we have a temperature gradient which is driving the heat flow. So heat is being carried out to the walls because of the temperature gradient. And so the heat flow is driven by the temperature gradient in this case. Oops, oh, I didn't mean to do that. There we go. And we can describe that system by looking at the entropy production, because we can think about it from the point of view of non-equilibrium thermodynamics. And based on the ideas of local thermodynamic equilibrium, we can write down an entropy balance equation where we have, in the green there, we've got the entropy flux, and in the other colour, which I really don't have a word for, beige or something, it's the entropy production. And the entropy production, you can see, consists of two terms for a single component system. We've got a term that's proportional to the temperature gradient and the heat flux, so it's bilinear in the flux and the field, or the driving force, thermodynamic driving force. So that's the entropy production due to heat flow. And then we have another term which is the entropy production due to the deformation of the material. So that's the viscous flow term in the entropy production. So that's all good. So what about in homogeneous shear? So in homogeneous shear, we have a very well-defined value of the density at all points in the system. The temperature is uniform, and we have no spatial gradients. So that means if there's no spatial gradients in anything, it means that we have to use homogeneous thermostats to remove heat from the system. And so the heat is removed uniformly right across the system with no spatial temperature gradients driving heat to the walls. So that raises a question. Does that mean that there's no entropy production due to heat flow? Because we have no spatial gradients of the temperature. So I'll leave that hanging because this is the central question that I really want to address in this talk. In our homogeneous shear simulations, this is with the slot algorithm, we have our equations of motion with the second one includes the homogeneous thermostat. Now I think I should have, is that the laser pointer? Yes. Sorry. So we have our homogeneous thermostat and that acts to keep the total kinetic temperature constant. But there are many other thermostats that we can apply. So this is the standard kinetic thermostat that we use in non-equilibrium MD very often, but this is not the only thermostat that we can apply. So the question is, how does energy flow through this system? How does it get removed? We know that the energy input to the system is through work done by the shear. So the shearing equations of motion produce energy dissipation, and that gives rise to viscous heating. And the energy output is via the homogeneous thermostat. The homogeneous thermostat, we can assume that that's like an external system that's at some temperature, which is equal to the temperature of the thing that we're thermostating, so the kinetic energy or whatever. But we know that temperature differences are required for heat transport. For a heat flux to occur, you really have to have a temperature difference. And in homogeneous shear, we've got no spatial temperature gradients. So instead, what we do know is that there are differences in temperature between different degrees of freedom. And that's where the temperature differences are. And I believe that that's where the entropy production occurs as well. So we can sort of understand all this through an idea of having different energy balance equations for the different degrees of freedom in the system. So for example, for the kinetic energy heat bath, let's say we only had two heat baths that we could define, a kinetic energy heat bath and a potential energy heat bath. And we could have heat transfer. So this would be the rate of heat transferred due to heat flux. Let's say we still had a spatially varying system. So we could have a rate of heat absorption at a point through the kinetic heat part of the heat flux. And we could have the heat generated in the kinetic degrees of freedom by the shear. And we could also have a term relating to energy transfer in and out of the kinetic energy heat bath. And likewise, we could have a similar equation for the energy balance of the potential energy bath. And in the steady state, we could postulate that there are extended Gibbs relations for the thermodynamics of this system, where we have a Gibbs equation for the kinetic energy bath and the potential energy bath. Now what that gives you when you work it through is an entropy production that's related to the temperature difference between the temperature of the potential energy heat bath and the kinetic energy heat bath. So if they differ, and if heat is being transferred from one to the other, then there'll be entropy production. And we can postulate that there's a constitutive relation, that that describes the rate of energy transfer between 2 degrees of freedom, and kappa here would be an energy transfer coefficient that plays a similar role to the thermal conductivity, but this is not. This is for internal degrees of freedom instead of spatial transport. So we conducted some simulations, and the aim of these was to determine the heat transfer coefficients so that we can use a model to predict temperature differences between the internal degrees of freedom, and watch how, when energy is applied to the system through work, through the viscous heating, energy goes into the system, there'll be temperature rises. The rate of temperature rise will depend on the rate at which energy is transported through the system, and that'll depend on these transport coefficients. So we'd like to determine those. And the simplest way to do it would be to control 1 degree of freedom to a different temperature from the others, and then just monitor the rate of heat transport between the degrees of freedom. So if we know the temperature difference between the 2 degrees of freedom, and we can calculate the rate of transport, then we can calculate the transport coefficient. So it sounds deceptively simple. We can calculate the internal energy fluxes and determine these heat transfer coefficients. And let's assume that we have 6 different heat baths. We can have X, Y, and Z kinetic heat baths, because we know that the momentum can be broken up into the X momentum, Y momentum, and the Z momentum, and that gives us 3 kinetic energy baths. And let's assume that we can do the same thing with the configurational degrees of freedom and the potential energy. So we can define directional temperatures for the kinetic energy and for the potential energy, and we can use this formula here that allows us to define a direction in phase space along which we do this derivative. Okay, so that's really what we're doing, is we're choosing a direction in the microscopic phase space in which we can go from one energy surface to another. So we have different energy surfaces and we can get to them in different directions in phase space. And each one of those actually ends up selecting a different temperature. So for example, we can have the 3 kinetic temperatures, TKX, TKY, and TKZ. And these are all things that can be calculated in a non-equilibrium MD simulation. And we can all do the same with the configurational degrees of freedom. These ones only depend on the positions, and we can calculate the X configurational temperature, the Y configurational temperature, and the Z configurational temperature. And Andras Baranyai was the first one to break them up in this way. I think the early work by Jeps and others just simply considered one configurational temperature, but Andras had the idea of breaking it up further into the 3 directional components. So we can control each of those with the thermostat. So the configurational degrees of freedom, so Karl will recognise this. Karl Travis responsible for defining the equations of motion for the configurational temperature that I'm describing here. And of course we can have kinetic thermostats for the kinetic temperatures. So we can control each one of those temperatures. These are with no shear on the system. We can also write down the internal energy balance, so we can work out the terms describing energy transfer from into and out of the kinetic energy. So our kinetic energy changes by we can work out the change by taking the derivative, and we end up with these terms. So this one, it turns out, also appears in the rate of change of the potential energy. So that means it's a conversion of one into the other. And this is transfer of kinetic energy out of the system into the thermostat. So each one of these is transferred to one of the thermostats. You can see that because that's a dot product, it can be broken up into the three directional terms. So it sort of makes sense that we have a dkx dt, a dky dt, and a dkz dt. Our potential energy looks very similar, but notice that this conversion term's got the opposite sign because energy that comes out of the kinetic degrees of freedom goes into the potential degrees of freedom. And we have transferred to the configurational thermostat as well. So we just did some simulations on a very simple system. It's just a few hundred WCA atoms at a typical liquid density. But the important thing here is that the temperature of the X kinetic degree of freedom was 2, whereas all other temperatures were constrained to be equal to 1. So in that case, heat should flow from the kinetic into the other degrees of freedom via the mechanisms that are possible through the internal energy balance equation. So this equation tells us what energy transfers are possible. So let's look and see what we get. So in this type 1 simulation, we have T1 on all of these degrees of freedom and T2 on this one, and that's higher than the others. Now there's no direct mechanism for energy to be transferred, say, from the X to the Y kinetic degrees of freedom, because the only energy conversion terms that we saw in the internal energy balance were between X kinetic and X potential, or Y kinetic and Y potential. So what we should see is energy transfer through here, but not sideways. And what we see is that when we look at all of the contributions to the energy balance, the overall energy balance is satisfied. So energy transferred in equals the net energy transferred out when we consider the energy transfers by all of the thermostats. However, we also saw that there are some energy transfers when there's no temperature difference. In other words, we're getting a flux between two heat baths that are at the same temperature. That just seems wrong. So these two are supposedly at T1, and yet there's a net heat flow from one to the other. Not only that, but the energy balances don't add up because the energy into this one is not the same as the energy out. So there must be additional energy transfers that I haven't taken into account through the energy balance equation. And when you calculate them, this is what you get. The red arrows show the direction of energy transport between these degrees of freedom through a mechanism that I can't see in the internal energy balance equation. There's another thing that's curious about this. There's instability in this system. If you try to run it at too high a temperature difference, the whole system crashes. The equations of motion get very, very stiff and the simulation dies. And to me, that indicates that there's too much constraint in the system. And we can see that because keeping Kx and Ky fixed also fixes the kinetic part of the first normal stress difference. So we're actually maintaining the system at a constant value of the first normal stress difference by constraining it in this way. So it actually seems quite unnatural to do that. We can do another simulation where we keep the configurational temperature, the X configurational temperature fixed at 1.5 and all of the others fixed at 1. And again, we get these energy transfers that are not seen when you work out the internal energy balance. And it's even more unstable. So that's why I had to do a temperature difference of 0.5 instead of 1. In another simulation, we actually applied steady shear at a shear rate of 1, keeping all of the temperatures at 1. And from the internal energy balance, when you include shear, you can calculate the energy input. So that's what I've put in red here. This is the energy input to the X kinetic degree of freedom, and this is the energy input into the X configurational degree of freedom through the internal energy balance equation. So overall, the energy balance works, but again, we're getting these energy transfers that I really can't account for. If we leave the kinetic temperatures uncontrolled to release some of the constraints, then again we still find these unaccounted for energy transfers. The overall energy balance adds up, but it doesn't seem to make sense, and we're still getting energy transport between degrees of freedom that are supposed to be at the same temperature. So it's all very puzzling, but we need to think again. First of all, let's go back to our idea of local thermodynamic equilibrium and ask ourselves, is it legitimate to separate the entropy? And entropy and temperature are intimately associated with each other because they occur as TDS in the energy balance. Can the entropy be separated into additive contributions? Well, yes, you can divide the Hamiltonian up additively, but notice there's no way you can split this potential energy. There's no obvious way to split it into X, Y, and Z components. And what you see there is that the distribution function factorizes, and therefore the entropy at equilibrium can be written as a sum of X, Y, and Z kinetic entropies and a potential entropy, an entropy associated with the configurational degrees of freedom, but that doesn't seem to be able to be divided up into X, Y, and Z components. So maybe it's illegitimate to do that and ill-advised. So what we see is that our overall energy balance is always satisfied in these simulations, but we see extra energy flows between configurational degrees of freedom and even between degrees of freedom that are supposed to be at the same temperature. So clearly there's something wrong either with our definition of the temperature or with the way that we've broken the energy up into different energy baths. We know that the potential energy is not separable in general into directional components. So maybe it doesn't make sense to treat it as 3 separate energy reservoirs. So we're going to do some simulations where we don't do that. It may be that a directional configurational temperature of itself doesn't exist, or it may be that the directional configurational temperatures don't correspond to the temperatures of the directional potential energy components. So maybe the temperatures are not actually assigned properly to the energy baths, and the temperature that I'm calculating, the configurational temperature, may not actually be the temperature of the potential energy heat bath. So that's where I'll leave it. I've probably confused everyone with that one. I'm certainly confused, but I'll be very happy to talk to people about it. And if anyone's interested in collaborating on this, I'd also be interested in talking to you. So thank you.
Thanks, Peter. Yeah, let's go ahead and use the applause icon. So, yeah, any questions? We have time for a few questions from the audience. Please remember to unmute yourself. Yeah, I guess I can kick off with a question, Peter. So, what's the when you're applying a shear and you have two solid walls, normally we would allow energy to transfer sort of naturally. Do you have any comments of applying further constraints inside the liquid when you're applying a shear on sort of what the negative aspect of constraints, of temperature constraints?
Yeah, so look, I generally speaking, I wouldn't apply thermostats to inhomogeneous systems if possible, because I think you mess with the inhomogeneity, which really is a natural emergent phenomenon, just like the other things that you're trying to observe in that system. And we know that it does change the value, for example, of the slip friction coefficient if you thermostat the fluid when you're doing inhomogeneous shear. So yes, it can mess with the properties that you're computing. So much better to thermostat the walls.
Thanks. Jesper, would you like to ask your question?
Yeah. I don't know if you can hear me.
Yes.
Yep.
Yeah. Thank you, Peter. So I was wondering, we know that the heat flux is also dependent on the strain rate squared, or the gradient of the strain rate squared. So where does this fit into this additional term in the heat flux vector?
Yeah, so that's for inhomogeneous systems. And what you can do, so you can actually redefine the temperature in Fourier's law by including the gradient of the squared strain rate into a non-equilibrium temperature. So there are two ways of thinking about it. One of them is that the temperature is modified by the shear, and the other one is that the heat flux constitutive equation is modified by adding a nonlinear coupling term.
Yeah, and I guess this nonlinear coupling term also works for homogeneous systems, right? Even in the presence of, as long as you have a gradient in the strain rate, then
yeah, but then there's a spatial gradient.
Yeah.
So it's inhomogeneous. The strain rate is not uniform.
Yeah, that's sensitive. Thank you.
Yeah.
Great. So we'll take the last question from Ian.
Thanks very much. This is a long shot, but I just wondered if the thermostats were disturbing your system in some way. You spoke of an instability, and that made me think that these isokinetic style thermostats might be just too strong, and possibly some kind of Langevin thermostat would be a more delicate way of maintaining the thermalization, the coupling to the heat baths. I just wondered that as a long shot.
Yeah, well, the thermostats definitely are constraining the system, and you can see that back here when you look at, say, the kinetic temperature. Do I define that? Up here. Yeah, when you look at your kinetic temperature, it's proportional, say, to pix squared. So this is the kinetic part of the pressure tensor, because it's a pix. And so if you constrain both of these temperatures to a fixed value, what you're really doing is constraining the first normal stress difference to a fixed value. Now, first normal stress difference really corresponds to a nonlinear flow effect. So what we're actually doing is it's a little bit like a Norton ensemble simulation, where you're inadvertently applying a normal stress to the system, even though you haven't got any flow. It's quite weird. So what you're doing is really squeezing the system, and eventually actually flow will result. So these thermostats are diabolical. If you have too many thermostats, you're actually constraining the system too much. That's my conclusion.
Okay, so do you think something more, a stochastic thermostat might be an avenue to explore?
I'm not sure that it's the mechanism of thermostating. I think it's the degrees of freedom that you're thermostating that's the problem. Too many degrees of freedom being constrained in any way, regardless of the thermostat type.
Okay. Well, thanks very much.
Can I just ask quickly? We've got a discussion session at 10. Peter, would you still be around then? If you
Yeah.
Fantastic. So the idea would be then there would be a kind of session where you can ask further questions.
Yeah, that's fine. Yeah.
Great. So thanks Peter again.
Thank you.
Let's move on to our next talk. And next up we've got Professor Billy Todd from Swinburne University of Technology. He'll be speaking to us about pumping of nano-confined water.
I need to stop sharing. But wow. I need to go to a different window in Shah.
I could just give you a talk again, Peter.
That's that's all right, Billy. I've figured out how it was on the other screen.
Right. Okay. Let me try and do the same here and share the screen. Right. Can everybody see that?
Yes.
Yep. Okay. Well, first of all, again, thanks very much, Ed, and to everybody involved in organizing this, and especially thank you for letting Peter and myself speak first from Australia. That helps us. That way we can have dinner at a reasonable time. So thanks again. So as Matthew said, I'm going to speak about something that we've been doing over the past few years, which is looking at how you can pump polar fluids, and water is perhaps the most famous polar fluid, by means of rotating electric fields. And I'll explain what that is as we go on. Over the years, there have been a number of people associated with this. A number of students, David Osler, Sergio De Luca, in particular, then postdoc Sridhar Kanam, who was a former student. Colleagues Federico Frascoli and of course Jesper and Peter are both here today as well. So acknowledgement to all of them who've contributed to this work over the past few years. So let me give an overview. I'll talk first about the physics behind the coupling of linear and spin angular momentum in fluids, just very, very briefly. I won't go into that in any depth at all. And then I'll describe how we can use this coupling to drive unidirectional flow via electrocoupling. So in other words, it's a different way of pumping polar fluids. And then I'll give a summary of some of the work that we've applied this idea to. So we've applied this to pumping of water between nanochannels, so planar channels. We've managed to show that you can do it inside of semi-functionalized carbon nanotubes and as well as semi-functionalized concentric carbon nanotubes. And then an important thing that we've recently published, and that is what is the efficiency of this mechanism? Because it might be a novel idea, but is it actually energy efficient? So we'll discuss that as well, and then just some brief conclusions. Okay, so the physics behind it, very, very intuitively. If you consider a simple Couette flow, for example, where you've got a fluid here confined to some solid walls, you move, let's say, the top wall by some velocity plus uw. And then, of course, you end up with your classic Couette flow, which is just a linear velocity profile. Now, let's say you have a molecule over here. Of course, if you've just got a simple atomistic fluid, then there is no spin, there's no rotation, and you just get a linear velocity profile. But if you've got molecules, then in addition, the molecules will spin. And you can just intuitively see how that would work, because let's say you have this molecule here in green. The molecule, of course, consists of atoms that are tethered. So because there's a velocity gradient, it means that this molecule here at the top close to the moving wall will move faster than the molecule, than the atom at the bottom. And so the molecule will tend to spin, to flip over on itself. And so you get spin, basically. So in addition to a linear streaming velocity, you also get a spin velocity. And that's really the key thing that's involved in this coupling mechanism. So in most practical applications of Navier-Stokes hydrodynamics, you just ignore the molecular structure of the fluid. Okay, so if you solve the Navier-Stokes equations for planar Couette flow, this is the expression that you get, and I'm sure you're all very familiar with it. And if you solve this, then you just get the classical linear velocity profile, where UW is the speed of the wall, the upper wall in this case, Ly is the length or the width of the channel, and of course Y is just the position. However, the formulation for the inclusion of molecular structure, that is the inclusion of spin and rotational viscosities, does exist. In fact, it's been known way back since Max Born's time in 1920. Snyder and Luchuk first, I guess, formalized it in terms of Navier-Stokes hydrodynamics in the 1960s. Evans and Street showed how you could calculate the associated transport coefficients back in the 1970s. And of course, there's a description of all this in the famous book, Non-Equilibrium Thermodynamics by de Groot and Mazur. Basically, what you get, though, is now instead of one simple differential equation governing the flow of linear momentum, you now get two. So you get an expression for the linear streaming velocity, if you like, or the linear streaming momentum, and you get an expression for the spin angular momentum as well. And these two equations are coupled, and they're coupled by this so-called rotational viscosity, eta r over here. So you can see in the top equation, this is the expression for the linear velocity, and that's coupled to the spin angular velocity here, and the coupling constant is this eta r coefficient. Likewise, the expression for the spin angular momentum also couples the linear velocity over here, and again, the coupling coefficient is this, this rotational viscosity. So one then solves these two coupled differential equations. So let's see how we can do that. Let's just say we're in the steady state, so there's no net acceleration, and the left-hand side just goes to zero of both equations. This term here tends to be, one can generally or often ignore them. You don't always ignore them, but in this case you can, because the so-called spin viscosities are quite substantially smaller than either the shear or the rotational viscosity. So this term goes. And then you can very easily solve this system of equations. And what you get is the same linear velocity profile as you would get if you ignored spin coupling altogether. But you also get an additional expression relating the spin angular velocity with the strain rate gamma dot. Okay, so, and the important thing is that this equation, this top one, is exactly the same solution you get by ignoring the spin coupling effects, which is why you don't really need to worry about them in macroscopic flows. And of course, Edberg, Evans and Morris showed this they simulated by homogeneous NEMD methods butane under a planar Couette flow, and they indeed did see this nice effect in the linear regime, where you find that the angular velocity is proportional to 1/2 of the strain rate. Okay, so that's the basic idea then. So now we ask ourselves, if shear can induce molecular rotation, can you flip this? So can you do the opposite? Can molecular rotation induce shear flow? And if you can do that, if there's a way that you can do it, then it suggests that there's a way that you can manipulate the flow of fluids without the need for mechanical pumping, as long as you can find a mechanism to rotate the molecules. And indeed, that is what you can do. And you can do it by applying a rotating electric field. Now, this was first proposed by Bontuis and colleagues back in 2009. Forgive me if I pronounce his name incorrectly. Some work that we did with Jesper, Peter, and myself back in 2010 also confirmed this. So what you can do, let's have a look here. We have a system of water molecules. Okay, so it's an electrically neutral system, but of course, each water molecule has a dipole moment associated with it. If we apply a rotating external electric field with some angle of, with some frequency omega, then the water molecules spin, but what they do is they then couple with the linear momentum and you end up with a velocity profile. Now that's given by the dashed line over here. Now, if the walls are the same, so it's the same material, what you end up with is equal and opposite flow. Okay, so you get half of the molecules moving to the right and the other half moving to the left. Unfortunately, that's no good if what you're interested in is pumping, okay, because that gives you zero net flow. So what do you do to solve this problem? Well, it's not that difficult. You just break the symmetry of the boundaries. So you have one surface that's say hydrophobic and another one that is hydrophilic, and then this velocity profile changes from what looks like kind of a distorted kink or a distorted S profile to one that is more traditionally looks like a Couette flow. Okay, so you actually do get a net uniform flow. So that's then the basic idea of the spin coupling. So now you can solve these equations either numerically or by non-equilibrium NEMD methods. And in fact, we've done both. And so what I'll do is I'll just show some results now. So here's some typical systems that we've looked at. So here we've got graphene sheets. So we've got basically symmetric boundary conditions. We put water molecules in it. We apply an external rotating electric field, and we can look at the velocity profiles, or we can break the symmetry. So here we've got one wall, which is hydrophobic, which is, you know, a graphene wall, and another which is hydrophilic. So in this case, it's a beta cristabolite, which is a kind of a silica wall. So it's hydrophilic. And so we break the symmetry. Again, we can put water molecules between them and apply an external rotating electric field. And what you get are profiles that look something like this. So here is our asymmetric situation. Here we've got a hydrophilic wall, and here we've got the hydrophobic wall. And as you can see, you can get linear velocity profiles. This is a velocity profile as a function of position within the channel. And for a fixed amplitude of the electric field, as you increase the frequency, you get greater and greater flow. For our symmetric walls, so here we've got two hydrophilic walls, you can see that we get equal and opposite flows. So we get flows going to the left on one half of the channel and flows going to the right. So if you sum them, you get zero net flow. You can compare these results with continuum theory as well. And if you do, so here's the analytic solution of those coupled extended Navier-Stokes equations. And here are some molecular dynamics simulation data. So the theory agrees very well with the simulation data. Now, very, very quickly, go through and show you that you can do the same with nanotubes. So you don't have to do it with just planar surfaces. So if we now functionalize a carbon nanotube and put in half of it with, we semi-functionalize half of it with carboxyl atoms to make it more hydrophilic, and the other half remains carbon nanotube, fill it with water, apply a rotating electric field. we can see that we get this kind of velocity map. So here we've got a 2% functionalization on the top half of the carbon nanotube over here. The flow is reduced in the top half, and it's more intense in the bottom half, as you can see with this velocity map. As you increase the functionalization, what happens, perhaps counterintuitively, when you think about it initially, you think, well, surely you increase the velocity flow, but in fact you don't, you decrease it. And the reason is that as you're increasing the functionalization, you're increasing the number of these carboxyl groups that are protruding into the nanotube itself. And they then tend to block the flow of water molecules. So there is a little bit of a sweet spot in terms of the degree of functionalization. This is just another way that you can view the velocity profile simply by binning the nanotube, and you see the same results, but presented in a different way. Another way we could do this is to look at water confined to concentric nanotubes, where the inside nanotube is functionalized with carboxyl groups. The outer one remains just a pure nanotube, and then you fill the gap with water. You apply the rotating electric field in the RZ plane, and you get a similar effect, okay? So you can find flow, and you can do it for different size nanotubes. You can do it for different degrees of functionalization. Okay, so that's then the basic idea and different systems that we've looked at. And now in the last few minutes, let me talk about the efficiency of this technique. So it was kind of neat to be able to show that this technique can work. But the question now that we have to ask is, well, it might be academically of interest, but is it actually going to be potentially useful? And in order to, one of the things that we needed to look at was, well, how energy efficient is it? And so that's then what this study is about. What is the efficiency of electropumping compared to, say, traditional planar Couette and planar Poisson flows? So the system that we look at is, again, a typical SPCE water molecule confined to atomistic graphene walls, either functionalized or unfunctionalized. We apply an electric field, rotating field of this form, so it's rotating in the XZ plane, and we perform NEMD simulations to generate all the flows and then calculate the efficiencies. So a little bit of theory. So now, again, Bontuis back in 2010, Bontuis and colleagues figured out what the theoretical energy dissipation or power for such a system driven by a rotating electric field would be. And they came up with this expression over here. Now, E is the electric field, mu I is the average dipole moment per water molecule. Nu is the electric field frequency. N is the number density. Okay, so this is the expression equation 10. They actually solved this theoretically, and I won't go through too much details with how they did it, but basically they got this expression here, equation 13. That was a nice simple expression for the average power dissipation for such a system. Now, it was a theoretical estimate, and it did not include the inhomogeneity of a highly confined fluid. They concluded that the method would be too power intensive. Okay, so in other words, you'd need very, very high intensity electric fields, and they just wouldn't be competitive in terms of being a useful technology. So they basically didn't bother any more than that. But this is the important thing, that their system ignored the inhomogeneity when you're looking at a system of something like water confined to planar nanochannels or nanotubes. So that may not be valid at substantially high degrees of confinement. And later on, I'll show you that that is indeed the case. So a more accurate numerical procedure would be to discretize that equation, equation 10, and perform NEMD simulations of the electropumping to extract the quantities of interest. And if you do that, you then get a discretized version of that expression, where here NT is basically the total time, length of your simulation, delta T is your time step, and the various mu's are the dipole moments of the water molecules at various different times. Okay. So if you integrate this expression over the whole fluid volume, it will give you the total power. So that's how we can do it for electropumping. What about Couette flow? Well, that's quite straightforward to do that. If you look at the rate of work on particle I by shearing force applied to the particle velocity VI, it's just this simple expression 15. Since we know that for Couette flow, the shear stress is a constant and is given by this expression here, where eta is the shear viscosity, VW is the velocity of the wall, then we get a simple expression for the force, which we can substitute into equation 15, and then we get our expression for the energy dissipation at position Z within the channel. So to get the total power, we just integrate over the whole channel, okay, over the whole channel height, and then we can get the total power for Couette flow. Similarly for Poisson flow, where now we just have some external field, like a gravity-like field, acting on the fluid particles. We drive the Poisson flow. We can calculate the shear stress exactly. Effectively, it's proportional to the integral of the number density, the fluid number density. You multiply that by the external field. And again, you get a nice simple expression for the power dissipation, which again, you integrate over the height of the channel to give you the total power. Okay, so then we've got three very simple expressions that we can calculate for the power dissipation. One for electropumping, one for Couette flow, and one for Poisson flow. So quickly, some results. So the way that we do it is that we do a simulation for electropumping. We choose a particular electric field intensity and frequency. We look at nanochannels of different widths. We look at the flow rate within the electropumping simulation. And then we do experiments for Couette flow, for functionalized Couette flow, and for Poisson flow, such that the flow rates are within 1% of what we got for electropumping, okay? So we adjust the other parameters accordingly so that we get flow rates within 1% of the electropumping. And that way we can be sure that we're comparing apples with apples, so to speak. So we're comparing systems that have the same flow rates within 1% error. Just a quick snapshot of the types of profiles that we get. So this one is typically what we get with electropumping for different nanochannel widths. For Poisson flow, remember we've got water confined to graphene, so that's a very hydrophobic system with very, very high degrees of slip, as you can see from the velocity profiles for the Poisson flow. We've got unfunctionalized Couette flow and functionalized Couette flow as well. Now, if you recall, this was the expression that Bontuis and colleagues derived for the average power from pure theory, okay? Didn't take into account the inhomogeneity of the system. How does that compare with the actual numerical results we get when we compare our electropumping simulations? And so this is what we've got. So this is what we actually measure in our NEMD simulations for various channel widths. And this is the theoretical value, which, as you can see, is just a single value because it doesn't take into account the degree of confinement. And so certainly for the narrowest channel width, we've got a difference of a factor of about 2.5 Okay, so they always said that their power dissipation was very high, and it is. But when you look at what you actually get, you're about 2.5 times smaller. So it's not as bad as what they first thought. And clearly, as you increase the channel width, the agreement becomes better, which is what you would expect. You would expect the theory and the actual simulation to converge in the limit as the channel width goes to infinity. That's what you'd expect. So now we have a comparison of the average power dissipations. This is what they look like for different nanochannel widths. We have functionalized Couette flow way down here. Unfunctionalized Couette flow in the sort of the beige color. Our electropumping is in the green, and Poisson flow is in the brown or orange. I think it's brown, really. So what you can see is that functionalized Couette gives you the lowest power dissipation. Then comes no functionalized Couette, then electropumping, then Poisson flow. If we look at the relative efficiencies with respect to electropumping, because that's the most, with respect to functionalized Couette flow, which is the most energy efficient, then we find that unfunctionalized Couette flow is about 34% that of the functionalized Couette. Electropumping is a lot worse. It's only 0.01% efficiency. But now this is the important thing. Poisson flow is 4 orders of magnitude even less efficient than electropumping. Now that surprised us substantially. We actually thought when we started this that electropumping would probably be the least energy efficient, but it's not. And how do people actually pump these sorts of, we're trying to force water through nanotubes. You're actually doing something akin to Poisson flow. You're actually putting some sort of pressure gradient onto the system to pump the water through it. You don't do it through Couette flow. And this is the point. Couette flow, while it might be more energetically efficient, is not actually a conventional means of pumping fluids. Now, maybe it can be devised as such. Maybe there are ingenious ways in which it can be done. But to my knowledge, for such nano-confined systems, that doesn't currently exist, that technology. So quickly, conclusions. So hopefully I've been able to show you that electropumping is this relatively new idea that we can use to pump molecules with a dipole moment, such as water, via coupling a rotating electric field with suitable asymmetric boundary conditions to generate unidirectional flow. It can be applied to planar geometries, but even to systems that are non-planar, such as nanotubes. We've shown what the relative efficiencies of the different schemes are, where Poisson flow is the worst compared to electropumping. And remember, the difference is about 4 orders of magnitude here. Then comes non-functionalized Couette flow, and the most efficient is functionalized Couette flow. And as I mentioned, while Couette flow might well be the most energy efficient, is it a suitable pumping mechanism? I'm not so sure that it is. But of the 2 more suitable pumping mechanisms, electropumping is certainly considerably more efficient than Poisson flow. As far as I'm aware, there are no laboratory experiments yet that have been performed to verify these results, but it would be really, really nice if that is one day verifiable. Certainly, NEMD simulations show it can be done. They've agreed with theory, so all that's missing now are the experiments to prove that it is so. And with that, I'll end the slideshow. So thank you very much for your attention.
Thanks, Billy. Very, very nice talk. Are there any quick questions?
I have a question. Hello?
Yeah.
Go ahead.
Can you hear me? Hi.
Yes.
Yes, I can hear you.
Thank you. It was a very interesting presentation, particularly for the fundamentals of the how you should think about the spin in fluids in general. So when we study fluid mechanics at the elementary level, we define the vorticity starting from a kinematic condition. The vorticity is defined based on the antisymmetric part of the velocity gradient tensor, irrespective of momentum or spin balances. Instead, you have shown that equality, the fact that the vorticity is related to 1/2 the shear rate, is a consequence of the spin equation in a very particular limit of rotational viscosity much smaller than the shear viscosity. So how can you reconcile the two views? One is purely kinematic, and the other one instead comes from a balance of torques.
Yeah. So what I'm talking about here in terms of spin is the molecular spin. So we're talking actually about the rotation of molecules itself. So the relationship is that the angular velocity, the spin angular velocity of the molecules is proportional to 1/2 of the strain rate. Okay, so that's really what I'm talking about. So the couple of Navier-Stokes equations really go down to, if I go back, I'm not sure if you can still see.
Yeah, we can still see.
Screen.
Yes.
You can still see. So it's these two expressions here. So this is a molecular level description. So what the S here is, it's the spin angular momentum equation that we're talking about. So now we're actually building in the fluid structure here. Okay. So we're not really talking about the macroscopic, if you like, vorticity of the fluids. We're talking about the molecular level description of the linear momentum, the linear streaming momentum, and the spin angular momentum of the systems.
Yes. So you mean that what I call vorticity is really is an ensemble or volume average over a certain parcel of fluid. Instead, what your omega is actually the rotation rate of a single molecule, and the two are in general different.
Well, it's still a field. It's still a field. So when we're looking at these things, we're averaging over all of the molecules, because remember that you've got the orbital angular velocity and the spin angular velocity, and the combination of those two give you the total angular momentum of the system. So here we're dealing with just the spin angular momentum of the system.
Mm-hmm.
Yeah.
But should I? So if I have a fluid that is not acted upon by external couples, so should I consider the rotational viscosity, or I don't remember how you call it, the spin viscosity?
It just depends what it is that you're interested in calculating. I mean, if you've got a system that's in equilibrium, then no. There's the average angular velocity is going to be 0. But if you apply an external field of some sort, then you will engender some sort of molecular rotation within the molecules themselves. But it really depends what it is that you're interested in looking at, what particular property of the system that you're interested in measuring. Because as you saw in these subsequent slides, that if you include this coupling of the spin angular momentum with the linear momentum, it makes no difference in terms of the solution to the linear velocity profile. You get exactly the same as what you would get if you ignore the spin coupling. So it just doesn't feature. That's why you never see this second equation in your conventional Navier-Stokes equations. This equation 3 never really appears. But if you're interested at the molecular level, then you need to include it. If you're actually interested in how the molecules themselves spin and the effect that that causes, then you need to include it.
I'm sorry to have to jump in, but we should probably continue this discussion in the discussion session. Let's thank Billy one more time and introduce our next speaker before the discussion. So next up, we've got Professor Zhang from the University of Beihang, and he'll be talking about multiscale simulation of droplet sweating and evaporation.
Hello, everyone. My name is Zhang from Beihang University. It's my big honor to give a talk on that. I think it's a good opportunity to communicate researchers in UK and other countries. So the talk today is about molecular dynamics and multiscale simulation of droplet wetting and evaporation. I think most of you know droplets are ubiquitous everywhere. In the rainy days, we can see a lot of droplets on windows leaves. For engineering applications, we can use droplets in spring cooling and inkjet printer. And we can even match droplets problem like de-icing problem when we take plane. My research about droplets actually is at the nanoscale. I think nowadays, because the improvement of nanotechnology, now we can generate droplets even down to the nanoscale. For instance, here is a research report from a research group in ETH. They reported that they can generate nanostructures on the surfaces using the print of nanodroplets. So even you study the macroscopic droplet, the droplet may be on the millimeter size, but the interface, like the liquid-gas interface and the three-phase contact line are on the nanoscale. So intrinsically, the droplet has a multiscale nature. So that's why we study using molecular dynamics and multiscale simulation. My personal research interest is like multiscale molecular dynamics and multiscale simulation. So the software where the computation code I use is the OpenFOAM. When I worked in UK from 2014 to 2017, I have the opportunity to be involved in a big project led by the Professor Jason Rees, and the group developed the multiscale simulation platform based on the OpenFOAM framework. I think most of you know that the OpenFOAM is a traditional CFD software, and based on this, the group developed the molecular dynamics code for liquids and also the DSMC code for gases, and we can also couple this code for the multiscale simulation problem. And today, I will talk my personal small work. I will use NEMD to simulate nanodroplets, and I also use the CFD solver, interform solver to simulate the dynamic wetting problem. I think the code now is free to be downloaded, and the organizer, Dr. Matthew Bodge, I think he is still maintaining and developing the code. So if you are interested in the code itself, you can contact him. And the main content I will talk about is 3 parts. The first one is the NEMD simulation of static wetting, and I will focus on the effect of the non-tension. And the second part is how to do multiscale simulation of dynamic wetting. I will talk about how to consider the slip model and the dynamic contact angle model. And the last part is the NEMD simulation of evaporation. And I will focus on the coffee rain effect and how to control it. So now next is the first part, the MD simulation of static wetting. In MD, and I think the most important thing is the pair potential. Because we simulate water droplets, so we use the TIP 4P 2005 model to simulate water. In this model, for each water molecule, there are 4 sites, one oxygen site without any charge, and 2 hydrogen sites with positive charge, and 1 manganese M site with negative charge. And the interactions between water molecules are based on both Lagrange potential and Coulombic forces, and the energy potential are applied between the oxygen sites, and the Coulombic forces are applied for all the sites have charges. And because we simulate droplet on platinum-like surfaces, so we need also the potential function for platinum. We use energy potential as well. As for the interaction between water and platinum, we use Lagrange potential as well, and we use the Lorentz-Besselot mixing rule to adjust the parameters, particularly here for the energy. For the energy, here is a scaling factor lambda. We use this to adjust the wetting property. Specifically, if lambda is 0.1 is hydrophobic case, if it's 0.25 is hydrophilic case, if it's larger, it's like completely wetting. So that's the potential function and the parameters we used for the simulation of water droplet and wetting problem. First, we look at the size dependence and the non-tension effect. We can use MD simulate different size of droplets, for instance, like here. And then we can measure the density contours for each droplet. And the liquid vapor interface are composed of the points. The points have half the liquid density, and then we use a circular fit to get to is made through to the points, and then extrapolated to the solid liquid dividing interface or the substrate. Here we can measure the contact angle. From a mechanical point of view, the contact angle actually is determined by the balance of 3 surface tensions of solid liquid, liquid vapor, and solid vapor. This balance is actually is governed by the Young's equation. I think all of you know this. But the problem is at the nanoscale, the validity of Young's equation remains an open question. A lot of MD simulations have demonstrated that the contact angle at the nanoscale significantly deviate from this prediction from Young's equation. One possible reason may be caused by the non-tension. The non-tension is the excess free energy exerted on the contact line. Because of the non-tension, so the Young's equation have to be modified like this. Here, tau is the non-tension. If we can see that if the non-tension is positive, the droplet will shrink and the contact angle will become bigger. Conversely, if the non-tension is negative, the droplet will spread and the contact angle becomes smaller. So based on this modified Young's equation, and we can do MD simulations first. For instance, for hydrophobic case, hydrophilic case, we both simulate 5 different cases of different size of droplets. we measure the contact angle, and then we draw the data, the cosine of the contact angle and the curvature of the contact line. If we do linear fitting to fit the data of NEMD data, and from the slope of the fitting line, we can actually determine the line tension. For these two cases, the line tension is the magnitude is on the order of 10 to minus 11, and then we can we draw the data on this figure. Here, this one and this one, we are our data, and we also put the data from the literature in this figure. As you can see, actually the data of the line tension are so scattered, even where the data are for water droplets on surfaces. So it means that the line tension is so sensitive, and maybe there are some reasons we need to figure out. One possible reason is that in the modified Young's equation, where the surface tensions actually are from the planar surfaces, we know that actually the curvature have some effect on the surface tension. So we can use this equation and to substitute to the modified Young's equation, and we can get a modified line tension. If we do this, we can modify the line tension a little bit, as shown in this figure. Actually, where the symbols shown in black color are the modified line tension. As you can see, the modified line tension is changed a little bit, but not too much. So where the data are still so scattered. So we believe that there are more critical reasons caused the scattering of the data. And the key point actually is caused by the position of the solid and liquid dividing interface. Because when we measure the contact angle, we need to define where is the interface. Here we use a delta H to define the distance above the topmost of the solid atoms. If delta H is 0, it's just on the solid surface. Here we use 3 different types of definition. Delta H equals 0, where sigma, or just 1 sigma or 2 sigma. As you can see, if we use different options of the solid liquid dividing interface, the determined line tension are significantly different. Not only the magnitude, but also the sign may be changed from positive to negative. So it means that in the modified Young's equation, actually tau is not the pure line tension, it's just the apparent line tension. And if we want to get the pure line tension, we need the complete definition. And this equation actually has been proposed in the previous literature. It's published in 2007. And we don't focus on the pure line tension. We just focus on the apparent line tension. It means that if you talk about apparent line tension, you need to give a definite explanation about how to choose the solid and liquid dividing interface. And on the other hand, if you only look at the focus on the contact angle at the macroscopic scale, so the pure line tension is not so important. You can just measure the contact angle at the nanoscale, and then you can do linear fitting and extrapolate it to the macro scale, and you can get the same macroscopic contact angle. It's fine. So this is the first part about the static wetting and how the line tension affects the contact angle. And the second part is how to simulate dynamic wetting. It's more complex than the static wetting. Of course, we can use NEMD to simulate a dynamic wetting problem, but the problem is NEMD is time consuming. If you want to simulate the whole dynamic wetting process, it will cost you a lot of time. So an efficient way is use the continuum simulation method, like VOF, volume of fluid method. In VOF, we need continuum equation, momentum equation, and we also need one equation of the volume fraction, RF. The volume fraction is 1 or 0 for the liquid or the gas region, and is in the region of 1 to 0 for the interface. So for the VOF simulation, now it's a standard method. I think everyone almost do the same thing, but the tricky thing is how to implement the boundary condition, because it's known that if you use theoretically, if you apply non-slip boundary condition, there is a shear stress singularity problem. So to remove the singularity problem, now a lot of models have been proposed, such as slip boundary condition and dynamic contact angle model. But we know that continuum numeric methods cannot provide this information by themselves. So we need what we have done is use molecular dynamics first, and then we derive some models and then plug into the VOF method. Specifically, what we have done is we use VOF to simulate the whole droplet spreading, but at the boundary, we use two types of boundary conditions, and in the center of solid liquid interface, we use the never slip. It's a standard slip model. But if we only use this model, here there's just one parameter called slip length. We can compare the VOF results to the NEMD results as shown in this figure. The black line is the NEMD data, is full NEMD simulations. And if we use VOF and without any slip model, as you can see, the spreading is much slower than NEMD. If we use the never slip, we can adjust the slip length, the parameter. But unfortunately, if we use the physical slip length, because for this case, we simulate a hydrophilic case, the slip length is very small. It's just 0.28 nanometer. As you can see, the spreading rate is still lower than the NEMD data. To match the NEMD data, we have to use an artificial, not very large slip length. Obviously, it's unphysical. The problem is that actually at the contact line region, there are a particular slip behavior. The slip is much larger than that predicted by the never slip. And here we use the slip model called MKT model. I will talk it afterwards. So what is MKT model? Actually, this MKT has been proposed maybe in 1960s, a long history, now has been applied in a variety of problems. And the principle of MKT is that the dynamics of the contact line actually is determined by the statistical kinetics of moleculars. When the contact line is at equilibrium, the frequencies of molecular displacement in the forward direction and in the backward direction are the same. So the contact line is static. But if the contact line, the equilibrium is broken, there is an uncompensated or unbalanced Young's force exerted on the contact line. Due to this force, the frequency in the forward direction is different from the backward direction, so the contact line can move. So the contact line velocity actually is equal to the mean free path multiplied by the difference between the frequencies in forward and backward direction. So according to the MKT theory, we can have the slip model like this, how the slip velocity caused by the difference from the dynamic contact angle and the static contact angle. And we can also use it inversely, how the dynamic contact angle is caused by the slip velocity. So some researchers use like this, and some researchers use dynamic contact angle, or some use both. So it's actually is an obstacle. What we have done is, and actually firstly, we use in this way, in the upper part, is we do this in 2017, because we know that now the dynamics of contact line is actually caused by the uncompensated Young's force. If the dynamic contact angle is different from the static, there is a force. And if there is a force, the contact line move has a velocity, and then the dynamic contact angle change. We can, because the contact angle change, we can change the curvature of the interface, and this changed at the boundary there. So the dynamic contact angle model can be applied in the VOF method. It's like this. But now we found that we can use it in an alternative way, because we can decompose the uncompensated Young's force into two parts, the dynamic effect and the equilibrium effect. Actually, the dynamic effect has been implemented in the VOF method automatically. It's like this. And we only need to supplement an additional source term into the momentum equation. It's like this. And in this way, actually, we can dismiss the dynamic contact angle. We can capture the curvature of the interface automatically. So to a brief summary for this method, this figure shows our strategy is like this. In the momentum equation, we add a source term is to account for the equilibrium effect for the contact angle. And for the slip, we have lever slip in the center and the MKT slip at the contact line. And we don't need any dynamic contact angle model, and the shape is automatically calculated based on the volume fraction actually. So now the left problem is how to determine the parameters in the MKT model and the slip length in the lever slip length model. So we use MD simulations. We can simulate different sizes of droplets, use MD, and we measure the density contours. We do the linear fit to measure the contact angle. We can get the contact radius. Here, we simulate 4 different sizes of droplets. After normalization, you can see the temporal evolution of the contact radius and the dynamic contact angle actually collapse onto one figure. And then we can do a polynomial fit to the temporal evolution of the base radius, and then we can determine the capillary number. And after we have all the data, MD data of static, dynamic contact angle, and the capillary number, we fit to the MKT model, and we can determine the parameters in this model. Actually, we use the dynamic contact angle model to fit, but when we use it in the VOF method, we don't use this. We just use the velocity of contact line in this way. So now we show the results. Actually, the left side is our pure MD simulations, and the right-hand side is our multiscale simulation. After we plot the slip boundary conditions into the VOF method, as you can see, the dynamic wetting process has a perfect match to the MD data. And this one is for the smooth surface. And even for the pinned surface, we can see that our multiscale simulation are also consistent with the MD simulations. And here we further compare different VOF solvers, and the highlighted solver actually is our present models. We use never slip, MKT slip, and the modified source term in the momentum equation. This one is the perfect one. We also simulate use previous version, like no slip or just never slip, or never slip, MKT slip, and MKT dynamic contact model in our previous papers. As you can see, the 5 solvers have different performances. Generally, the solver 3 and 5 has the best performance. But the other solvers, the spreading rate is lower than MD data. So from this, we can conclude that the solver 5, that is our present method, has the best performers and also have consistent theoretical foundation. Now I will talk about the last part, droplet evaporation and deposit pattern.
Jun, sorry to interrupt. Would you be able to conclude at some stage?
Sorry?
Would you be able to conclude? Because we're running out of time at the moment. So could maybe 2 minutes or 3 minutes? Is that
okay?
Is that
No
right?
problem. Okay. I will, yeah. Okay. So the last part is about droplet evaporation. We focused on the deposit pattern. Maybe I think all of you know the coffee rain effect. Here we just do MD simulations of salt water evaporation, because the water, if we increase the temperature of the surface, the water will be evaporated and the salt ions will be deposited on the surface. And here I can show some different patterns. As you can see, we simulate different salt concentrations and different ramp rate and how quick the temperature increase. As you can see, if the ramp rate is quicker, and actually we get the clamp pattern. But if the evaporation is slower, we can get the rain-like pattern. And the reason behind this is that in the evaporation, there is a pinned stage and the contact line is pinned on the surface, and there is an internal flow from the center to the rim. Because of this flow, the salt ions can flow from the center to the rim and finally form the ring-like pattern. And we use MD to explain how the phenomenon is formed, and then we use the electric field to control the patterns. Because of the time, I just use this one to conclude what we have found. If we use an AC electric field, actually we can adjust the ring-like pattern to a clamp. If we use DC electric field, we can change it to a ribbon. And this is we use the electrowetting to control the patterns. And we can also, besides the MD simulation about droplets, I'm also doing some DSMC simulations and some applications for the rarefied gas flows in aerospace engineering. I'm also doing some data-driven discovery, and maybe we can discuss later. Okay, thank you for your attention.
Thanks also for speeding up at the end.
So thank you to the organisers, Ed and Borg, for giving me the opportunity to speak at this interesting meeting. And good morning, good afternoon, and good evening. I think that basically covers all time zones. So what I'd like to do today is talk about 3 interesting applications of the Doll's tensor algorithm. So let's get straight in. So is that okay? Has the next slide moved on?
Yes.
Excellent, because sometimes there's a lag, that's all. Okay, so let's begin. So the Doll's tensor Hamiltonian, as we can see here, was introduced over 40 years ago now by Bill Hoover and colleagues. And H naught here is the unperturbed Hamiltonian. And what you do is you couple your Hamiltonian system to an external field, and the resulting Hamiltonian takes this form. Notice there's a dyadic, a second rank tensor QP, and it's that gives Doll's tensor its name, after the QP doll that you can see on the right hand side. You don't see many of these around these days, but that's where originally the name of the method came from. So here we have a double tensor contraction into a strain rate tensor. T here is the transpose, and that Hamiltonian generates the following equations of motion for the rate of change of generalized position, the Q dot equation, and the rate of change of generalized momentum, or the P dot equation. We'll leave del U or grad U undetermined at the moment. And the point is that you can generate all sorts of interesting flows from that general Hamiltonian form. Originally, it was, back in the early 80s anyway, it was introduced mainly to study planar Couette flow. And we've heard quite a bit about that from Billy and Peter already, planar Couette flow. But then it was soon realized that while the Doll's tensor equations could generate planar Couette flow and give the right results in the linear regime, when we went to nonlinear regime, it didn't agree with the homogeneous shear or sliding brick method. So there's something wrong. And it turned out that you needed to just simply transpose the P dot equation, and hence they transposed the letters, and it became the Slod algorithm rather than Doll's. But that was the only instance where it didn't seem to work. For all other intents and purposes, it's fine as an algorithm, or if you stick to the linear regime. And you can do much more with it. And I'll give you now 3 applications of where you can use Doll's tensor. So the first application is fragmentation of liquids. This is a topic I spoke about at Dennis's 60th birthday in Obergurgl in Austria a few years back. You can stretch a liquid. In other words, you can place a liquid under tension or negative pressure. You can do that by, for example, isochoric cooling into the negative pressure region. But once you've done that, it'll become metastable with respect to cavitation. Okay, so you can get interesting phenomena, and liquid will break up into droplets. Some of these droplets may be solid, so you get a mixture of solid, liquid, and vapor. And this has got interesting applications. One particular application is in dumping of fuel from aircrafts. So I don't know what's happened there. Right, so sometimes what the problem is to try and understand the size and shape distribution of the molecular particles or clusters. So in 1988, Brad Holey and Grady came up with a clever little algorithm to simulate liquid fragmentation. Okay, the problem is quite complex. You could do it with the continuum mechanics, CFD, and various other things, but it's such a complex problem that simulation or molecular dynamics or particulate simulation really comes into its own. So what's this algorithm? Well, you take a periodic simulation box. Here it's illustrated in 2 dimensions, fully periodic, and you simply undergo uniform dilation. So you stretch it. You do that by imposing a velocity profile at time 0, and thereafter the expansion's adiabatic. You grow the box lengths. In this case, it's a square cell, so each side length is the same, as a function of time. So you take L of t is the original time 0 box length, and you multiply it by 1 plus eta dot t. Eta dot is the strain rate. And I said that you had to augment the velocities at time 0, so you take the thermal components of velocities and you add on this contribution here that accounts for the fact that it's expanding. So you do that at time 0. It's reminiscent of the way we used to do planar co-wet flow before SLOD and DOLS came along. You did it through the periodic boundary conditions, the so-called Lees-Edwards sliding brick periodic boundary conditions, and you just waited for the flow to develop. The DOLS tensor, on the other hand, does it through the equations of motion, and you can do more complicated situations with time-dependent flows. Now, in addition to this, once a particle crosses the periodic boundary condition, remember that the periodic boundary condition is changing in time, you have to fix the velocity and change it to an appropriate value when it comes back in the other side. So that's the essence of the Holey-Grady algorithm. And what can you do with that algorithm? Well, if you start with a square patch of fluid, in this case it's a Leonard-Jones spline potential, again it's 2 dimensions, it's easier to visualize in 2 dimensions. If you start off from a density of 0.75 and t equals 0.6, these are in Leonard-Jones reduced units, and you stretch it at a rate 0.107, quite why it's that particular value, I'm not quite sure, but that's what they chose. And then what you do is you stop the simulation at some particular difference in box length or box area or volume, whatever you want to call it, and you examine the contents. So here what we find is the temperature's dropped to 0.39. Remember, it's adiabatic, and the density has now gone down to 0.175. In fact, you engineered it so it ends up at that density. And you can see that the liquids broke up into fragments of various sizes. Now, one of the things I was interested in back when I gave this talk at Obergurgel is in looking at the mechanism of fragmentation. And the question I was interested in is the mechanism of fragmentation the same or different to that of spinodal decomposition? Just bear with me a moment. So the way I did that is by taking a box, equilibrated box of fluid, expanding it at one particular rate, I think it was the same rate, 0.1, and then following an expansion pathway through the phase diagram. So the black curve is the expansion pathway. The blue curves there represent the best I knew at that time in history of the liquid vapor dome in the phase diagrams. This is a T-row plane. The black line there is the an attempt to find the critical point, rectilinear diameters construction, and the horizontal black line down at the bottom is my estimate of the triple line. So you follow the trajectory as it goes in. It goes under this gas solid line into the liquid vapor region and finishes at that orange coloured circle. And here are a sequence of, oops, it's gone on to the other one, a sequence of snapshots from the expansion pathway labelled up at each of the different coloured circles as we move from right to left. And you can see the final snapshot looks like the one on the previous page. So then what I did is took equilibrium conditions to equilibrium molecular dynamics, sampled some of these points. I don't know why it keeps moving on, whether I'm doing it or someone else is doing it, and did the equilibrium simulations at those state points and compared them along this pathway, and you can see that qualitatively, at least, they look quite different. Quantitatively, the way you would do this, and the way I did it back then, is by counting clusters and performing some cluster statistics. These are Stillinger clusters, and then you can show that the mean fragment size is quite different, the fragment distribution is quite different along these two different pathways. Now, I said this was all about Doll's tensor, and when I gave that talk at Obergurgel, I think it was Billy Todd, who came up to me and said, actually, that what you've described sounds a bit like Doll's tensor. And I thought about it, I thought, well, it does, and that would make a more suitable way of doing the simulation rather than the Holy and Grady method. And so I set about just trying to do it by Doll's tensor. And the way this is done is set the strain rate tensor equal to epsilon dot times the Kronecker delta tensor. I've deliberately put epsilon dot not the same as eta dot on the last slide. I'll come back to that in a moment. It's not the same thing. Here's my basic Doll's tensor equations of motion with that strain rate tensor. That's for the Q and the P. Okay, but we're not complete. We need another equation. So we need an equation for how the volume, or area if you like, in 2 dimensions changes with time. I'm just going to loosely flip between area and volume. So if we write down the equation for a cold system of particles with no momentum and non-interacting, we'd end up with Qi dot is epsilon dot Qi. We can solve that differential equation. That shows us that the coordinates go with time exponentially. They expand exponentially with time. So if we imagine taking a particle, if we come down to the left-hand corner here, we've got a simulation box. This light blue square is our original box at time 0. Let's pick a particle right on the edge, the top right corner of the box with coordinates q, x0, q, y0. Let's expand the box to this bigger grey coloured box, if that's the right, beige, I don't know. But then the particle moves to this new position, and given you know that how the coordinates change with time, you can work out what the volume scale's like, and it goes like e to the 2 eta dot t. And therefore, you can recognise that that's the solution of the following differential equation. V dot is 2e dot v. And in 3D, it'd be 3 rather than 2. So you've now got a complete set of equations to model fragmentation in the same way that Holy and Grady did it. Now, you have to be careful here, because I did mention that I'd used a different symbol for the stretch rate or strain rate. In Holy and Grady's original technique, they had growing periodic box lengths, and they used eta dot. I've used epsilon dot. What's the difference between them? Well, it turns out one's related to engineering strain and the other to logarithmic strain. So there's just a logarithmic connection between the two. So you still need periodic boundary conditions, as you do with slot of wet flow. Some people a while back thought that you could introduce a form of slot, I think they call it P slot or G slot, where you could do it without the periodic Lee-Edwards periodic boundary conditions, and quickly realised that that's nonsense. And indeed, it's the same here with fragmentation. You still have to use the expanding boundaries, but you have an equation of motion that tells you how those boundaries change with time. You don't need now to augment the velocities at time 0, and you don't need to do anything about the velocities when particles cross periodic boundary conditions, because the momenta that appear in those Doll's equations are peculiar with respect to the expanding flow. So it's very easy. Now you've got a periodic system with peculiar momenta to calculate temperature and pressure. Okay. So here's a qualitative picture of what happens. On the left-hand side, we've got epsilon dot is 0.0727. That's equivalent to Olean and Grady's 0.107 for their eta dot. And you can see the pictures look qualitatively the same. Some of you will argue, well, that's just a picture. You can argue anything from a picture. But when you do the cluster analysis, you find that the mean fragment masses are equivalent. There is an error bar associated with that, and I've worked up quite a lot of data, but I haven't got time to get into it. I can assure you that they give identical results within the statistical uncertainties. So that's got an interesting application. Another interesting application with a different motivation. I was interested in looking at fracture, solid fracture, so ball plate penetration. I'm doing some work with Puneet Patra at the moment and his PhD student on this. But at the time, I was looking for a way to parameterize SPH, smooth particle hydrodynamics, from molecular dynamics. We wanted a way to find out Young's modulus, the yield strength, and the ultimate tensile strength for any given pair potential. Now, the way you do that in a real experiment for a real material, not talking about pair potentials, is to do a tensile test, and then from the stress strain curve you could get those numbers. So I wondered if I could do this by molecular dynamics, looked in the literature, and you can find discussions on various algorithms in there. I've labelled them 1 to 4. The first one is the so-called naive approach, where you've got your simulation box with molecular dynamics particles representing a solid. It doesn't have to be a triangular lattice, I've just drawn it like that. And you apply an external force, but where do you apply it? Well, you can apply it to the end particles at the edges. That's the most obvious thing to do, but that quickly can lead to failure. Not the failure you want, as you'll see if you try that. I then saw that in Bill Hoover's textbook, he did it in a much more cleverer way. He applied the forces in a piecewise form that grew linearly with time, and the maximum of the force is about 2/3 of the way along the test specimen. Okay, this test specimen is supposed to represent a dog bone shaped specimen there. That's why I've shaded it in that way. And then another way, which is the way I did it with a student, Tom Hiddleston, we did it with stretching periodic boundaries in the same way that I talked about the fragmentation, but now only in one direction. So how do you do this by Doll's tensor? This is method 4. Well, you'd write your strain rate tensor in the following way. So you've got EXX dot as the first non-vanishing, the only non-vanishing element. That leads to equations of motion. Again, I'm in 2D. You can easily extend this to 3D. And you can see the extra terms going to the X dot and the PX dot. And then you've got the form for the only expanding box length. The Y box length stays the same, and it's only periodic in the X. So if we start from a triangular lattice with a density of √4/3, so all the particles are unit spacing apart, using a pair potential that Bill Hoover first introduced, and I'm fond of quite using because I know the phase diagram for this material. 2 minus r squared to the 8th minus 2 into 2 minus r squared to the 4th, valid for r squared less than 2, so it's quite short range, very smooth, and very cheap to compute. You don't have to mess around with long range corrections. Now, being homogeneous, you can use the zero wave vector stress, microscopic stress tensor to calculate the stress. So just usual expression from the virial. And the strain here, it's easiest to calculate the engineering strain from the difference of the box length at any time t relative to its time 0. You can also calculate the stress using method of planes or smooth particle averaging, which is why I do it today, and you can calculate the central plane and look at momentum flux across that plane, and that's the way I also did it. So here's some results. I've nearly finished, so if I'm sailing close to time, don't worry. Here's the results on the left-hand side from Hoover's method, the piecewise additive force. Here we've got a rectangular bar that we pull apart under tension with applying these external forces, and you can see that the bar breaks. It's brittle fracture, as you'd expect with these simulations. Down at the bottom, if you look at the bottom right on the left-hand side, we've got a stress-strain curve, and we can see that it goes up to about 6. It's 6 in Hoover's book. It's 6 pretty much, and then it fails at a 10% strain. That's typical of brittle fracture. Then if we look at the stress profile calculated with method of planes, we can see that the stress is anything but uniform in the X and the Y. But the value at the central plane at X equals 0 is 6, which corresponds to the value we've shown here. Now on the right-hand panel, I'm showing snapshots of the failure. I would do if it has not gone on. Using the periodic boundary conditions alone, in other words, the one that I showed you with Hiddleston, and then in method 4, where we've done it with Doll's tensor. While the breaks at the left and right hand edges, you can't control exactly where it breaks. It's very similar to each other. The mechanism looks slightly different from Hoover's method, but there's no way of telling which is the correct one unless you compared with real experimental data. But the pure periodic boundary and the Dolls are certainly consistent. Now, importantly, when we look down at the bottom, what we see is now the stress profile is uniform in both the X and the Y. It doesn't vary with X. The engineering stress strain curve shows again the failure at 6, and then all this noise down here, which I cut out from the previous example, is where the material is broken apart into 2 pieces. So you can get the elastic modulus from the linear portion, the slope of the linear portion. The ultimate tensile strength is obtained from the point where it's stress at which it fails, and the yield strength, you put a tangent to the elastic portion, you move it along the axis to 0.2% engineering strain, and you read off the value of the stress. So you have a convenient way there of getting all the parameters you want. It's spatially homogeneous, and you don't have to do anything funny about velocities when they cross boundary conditions or setting them at time 0. And you've got the benefit of it's all through the equations of motion, so you can do the theory with this, and the connection with linear response theory is there. Very quickly, I'll finish on the very last application. It's very much related. The motivation here was to look at closed die forging of metals, and I wanted my student to get a first understanding of uniaxial compression by looking at uniaxial compression of a gas. And so just by reversing the expansion rate, so it becomes negative, you can, and coupling the equations to an Jose-Hoover thermostat, you can then simulate uniaxial compression and expansion, as well as adiabatic expansion and compression if you knock off the thermostat. So you can use that to generate a Carnot cycle. I've developed this as a teaching tool, actually. This is hot off the press. So you can start at a certain particular equilibrated system. I then underwent isothermal expansion, that's the red curve here, then adiabatic expansion, then isothermal compression, and then finally the black curve, taking it right back to the start, is adiabatic compression. The point is that you can control the expansion rate perfectly. So if you do it sufficiently slowly, each leg of the run is essentially reversible. So you've got your Carnot cycle, and here's just the temperature chart, flat temperature in the isothermal expansion, and the 2 sloping lines are the adiabatics, and the green again is the isothermal. So I haven't even had time to think about this. It's just what I did as a teaching tool for my thermodynamics course, which is coming up very soon. So in conclusion then, the Doll's tensor Hamiltonian, introduced over 40 years ago, is highly versatile, can be used to simulate many interesting NEMD problems. You can use the method for time-dependent flows, and it also facilitates theoretical work, having the perturbation built into the equations of motion rather than through just the boundary conditions. And the thermostating is simpler, with all the problems that Peter's mentioned earlier that go with deciding whether to do it kinetically or configurationally, etc. And I've introduced 3 applications: behavior of liquids under tension or fragmentation, solids under tension or the tension test, and uniaxial expansion and compression of a gas. There are many, many other applications for dolls, but there's just 3 that I thought were interesting and dug back into my archives and fitted into a short 15-minute talk. Right, thank you for your attention.
Thanks, Karl.
I'll just see if I can get rid of that. Yes, there we go.
Do we have any questions? I can probably start off. Are you able to go back to the image where you had the tension of the? I think it's slide 16. I can see
16.
Yeah.
Yeah.
Do you have periodic boundaries in the sort of transverse direction to pulling?
No, there are no periodic boundary. What happened when I tried periodic boundary conditions in the y direction as well is that the material slipped along lines. It didn't look physically reasonable, and so that's where I went to dropping the periodic boundary conditions in the y direction. Okay.
Mm-hmm. And you don't get the Poisson's sort of
no. You can't get Poisson's ratio from this.
Yeah,
it's
exactly.
Pure uniaxial tension with no change in the y direction.
Have you maybe tried? We've tried this displacement method where you take regions on the side, right, and you just displace them by a bit. Let it equilibrate and repeat it, sort of mimicking how you would do this in an experiment. Have you tried that technique?
No, I haven't, and that sounds interesting.
So we've published some work on graphene. How do you test the sheets? But these nets already exist and have been existing. So basically, you take a region and you displace it, and you let it equilibrate. So no, you don't apply these terms to the Lagrangian or Hamiltonian. It's a very simple an NVT or NVE simulation. And you keep repeating this. It takes longer because you need that equilibration. You need it to occur.
Yeah, well, this was more of a pragmatic tool to just generate some constants, some parameters I needed for an SPH simulation. But
yeah, one more comment, and I'll pass over to Peter. Have you heard of peridynamics before?
Yes.
So that could be, I think, slightly better than SPH if you're interested. All right, Peter, go ahead and ask a question.
Yeah, just a quick one. Karl, I really liked your Carnot cycle simulation. Yeah, that looks really neat. I guess you can study finite time processes too. Then you can look at differences between fast cycles and slow cycles. And
yes, you could do.
Yeah, and look at irreversibility.
Yeah, the full ramifications of this haven't sunk in yet because I only did it. I finished this on Saturday. It was just something I was thinking about the teaching application. Nothing more time.
You've got a tiny difference between your two temperatures, really, haven't you? That it'd look a lot nicer if you had a bigger difference in the temperatures, I think.
Yes.
Carnot cycles are shocking for the amount of work you get per cycle. You can see it there, can't you?
Yeah.
No wonder they're not practical. Yeah, I just wanted to comment on that. Yeah, it looks really nice, Karl. Thank you.
Hello, yeah, thank you very much. And thanks for organizing such a nice workshop meeting. Can you see the slides by now?
Yes.
Okay, cool. Yeah, so what I'm really presenting is part of a PhD work of Ahmad Mokhimi Khairabadi, excellent student at ETH Zurich. Unfortunately, I think we lost him to industry by now, or very soon. Anyway, this was supervised by Leonard Sagis, who is a professor at Wageningen University and an expert in surface rheology. Martin Kröger, probably well known in the NEMD community, and whatever I did in this business. So interface rheology, we haven't heard so much today, and it's a rather maybe a newer field. And maybe I should briefly clarify or motivate that there is some relevance to it. I took this from a review from Jan Vermand and Patrick Andersen this year. So they distinguish between relevance in society. For example, lung surfactant is an obvious example where the properties of the interface and how this thing flows is very important. Of course, in your eye, the tear film stability or other biofilms, very important. And unfortunately, aerosol emissions, these type of things are a lot of talked about recently. Of course, industry has also some interest in these things, the whole stuff about foaming, blending, emulsification, also to some extent 3D printing, encapsulating stuff, things. There's relevance of this interfacial rheology. Okay, so how do the experimentalists do that? And it's rather new, sorry. And I think it's fair to say they are still figuring out how to best measure it, because we cannot use our cone and plate devices because you want to measure the rheology of the interface. And so one thing is you take a Langmuir trough and you put a rod here, you make it magnetic, and so you can move it with a magnetic field in plane, and then you measure how much this thing moves for a given perturbation and work out the interface stress from this one. The bicone in the middle is something closer to a usual rheometer, but what you try to do is you try to shear only the interface. So you have a bicone with a tiny, tiny opening angle. You want to place it right at the interface, and then just do a rotational rheometry on the interface. This is also commercially now from Anton Parr, and a double wall ring experiment where you're trying to do the same, but you have a better defined flow because you have these double wall ring. Anyway, so the message here is that it's new, and experimentalists are still more or less trying to figure out how to do it best. In simulation, we have, of course, way more freedom, so maybe we can do it better or easier. So how can we do that with non-equilibrium molecular dynamics? Well, the challenge is we want to apply just the deformation in the plane. Yeah? So only to the interface. Why is that important? We want to avoid the contribution from the bulk. And the problem is that the bulk contribution is huge. Yeah? Because you have way more material, and typically what you measure is dilatational moduli. And so the bulk being nearly incompressible gives a monstrous huge contribution compared to the tiny one from the interface. So basically, the simulations face this very same challenges as the experimentalists, unfortunately. But we hope to benefit still from simulations being way more flexible, right? We can invent some stuff. So we do molecular simulation. So briefly introduce the model. You won't be surprised. You have a Lennard-Jones part here, and we're looking at polymeric molecules. So we have a bonding potential. For the experts, this is just the Krämer-Gress standard model. In addition, we have explicit solvent, which for simplicity, we take Lennard-Jones like, not like Lennard-Jones particle, and say they are water-like, which just means our Lennard-Jones interaction parameter is 1. The polymers, the surfactants we are looking at are called pluronics. So they are copolymers, and they are symmetric. They have 3 blocks, one PEO block, then a central block of PPO, and then again PEO. The idea is that both ends are hydrophilic and the central block is hydrophobic. So what you imagine is you have a kind of a hairpin where both ends want to stick into the water. We model this by different values of the Lennard-Jones interaction parameters with the water molecules. We look at rather short chains of 50 beads and have a reasonable sized simulation. We do that at the Lennard-Jones gas-liquid coexistence point so that we have a liquid-vapor interface. So the molecules we are looking at, we take 2 of them. One on the left, one has 21 hydrophilic beads and a shorter middle bead, whereas the one on the right, it's the opposite, shorter heads and a longer middle. These pluronics we took because they are commercially available, and Ahmad wants to do some experiments as well, so that's very convenient. And they are used as emulsifiers, detergents, etc. So they actually have some use, and they are sufficiently simple. Okay, so before we go in any rheology, because it's probably a good idea to look at these things in equilibrium. So polymers at interfaces is a talk in itself. Most polymers are surface active, and the idea why these things like to go to the interface go back to Pieransky in the 80s. Basically, the idea is these molecules, if they go to the interface, they take out a certain amount of surface area, and that reduces the interface tension, just because you have less interface between, let's say now, water and vapor exposed. And if you have polymers, then the relevant length scale is the duration radius parallel to the interface. And because polymers are flexible, deformable, what you expect is that you get some pancake-like structures, that they take out as much interface area as possible, meaning as entropy allows them. And so we see that the effective interface tension is modified quite a bit. And this is on the right versus the interfacial area concentration there. Okay, So what we see is that we have these deformed conformations. And also you have a 2D structure formation then of these polymers. There are some snapshots on the left, and we did some Grand canonical Monte Carlo simulation and also some density functional theory to work out what would be the effective gas-liquid coexistence of these beasts. That's not of relevance for this talk, but what is relevant is a slow relaxation that we see in equilibrium dynamics, that this is the end-to-end vector correlation function of these two pluronic molecules at such an interface, and they are slowly relaxing indeed. Okay, so now finally coming to the rheology. How do we do that? So again, the problem is you want to only deform the interface and not the bulk, and you want to compress it. And so our idea was to use semi-permeable moving barriers. So on the left, you have a snapshot of the system. In gray is the water molecules. So we have a liquid phase down here, a vapor phase up here, and we have our pluronic molecules at the interface, the hydrophilic ones pointing inside and the hydrophobic ones on the surface. So that's how it should be. And so we have a total lateral length, say L0, and now we have these barriers that we move with a prescribed frequency omega and an amplitude small L0. And these barriers are permeable to water, but do not allow the polymeric beads to cross. So in this sense, they are semi-permeable. And what we do is effectively the polymers that are confined there, they see an interface area available to them that is periodically changing in time by an amount delta A. So the relative area change is then controlled by the amplitude with which we move the semi-permeable barrier divided by the bare length L0. And okay, we want to have this relatively small to 1 to be able to compare to experiments. Okay, so that's the setup of the simulations. Below you see snapshots of the simulation, and highlighted here are one of these chains, and indeed is what you expect. You have these hairpins pointing into the water, and then a small bridge of the hydrophobic midtail, whereas in the other pluronic, because the heads are smaller, this is less pronounced, and you see characteristic differences here. So I've explained how we impose the deformation. How do we compute stresses? This we do by explicitly calculating the force that is exerted on the barrier, and from the difference to the reference state, this is the excess or the extra dilatational surface stress that we find on these barriers. Then we want to be in the linear response regime, and so be able to relate this surface stress to surface dilatational moduli, which are denoted by capital E. And as usual, we distinguish the real and imaginary part of that. Why don't we do shear if this thing is so complicated? Of course we did shear. That's the thing we did first, and we verified that we get a reasonably linear profile. The problem is that in almost all experiments you see close to 0 stress responses in this. The signals are simply too weak so to make any reasonable connection from the simulation to the experiments. So we have to go to dilational. All right, so here are some results for the dilatational moduli E prime and E double prime as a function of Deborah number, which is just a measure for the frequency of the deformation times the characteristic relaxation time of the molecules. And on the left and on the right, you have the different systems. What we find very characteristically for both of these molecules and also for different concentrations is a regime, rather extended regime, I would say, where the moduli increase with the square root of the frequency. This is a bit puzzling. I mean, this is first of all very different from what we are used from bulk polymers, which go linear and quadratically. And so, of course, we would like to have something like a Maxwell model or a simple constitutive model describing that. For the experts, there is, in fact, a constitutive model claiming a square root of frequency dependence here. That is Lucas and Van Tempel. But the thing is that they have a completely different mechanism that is absent in our simulation. So we can have apparently coincidence, but for the wrong reason, let's say. If we try to compare to the experiments, well, this is semi-quantitative. Unfortunately, we were not even possible to go down in frequency that much as we thought. There is a tendency to see this square root of omega behavior at small frequency before anything else happens at lambda. So this is certainly not understood. I think simulations would be very helpful in better understanding what's going on here, why some molecules are more efficient in reducing interface tension and for user application, than others, for example. One tiny first step that we did in the direction was trying to relate structure and rheology. So on the left, you see the surface stress, which is the extra dilatational stress versus the area change. So on the very left, so these are the linear response regime, very tiny deformations, and then up to 10 and 20% area change, which is quite in the nonlinear regime. And we also measured the change on the right-hand side, the change in the gyration radius, the in-plane component of that. And if we plot them parametrically against each other, we find that they are nicely linearly related, which gives us some hope that maybe a relatively simple constitutive relation can be found for this interfacial rheology business. Okay, so this brings me to the end. I want to thank Hans-Christian Oettinger and his group where is Ahmad and was this performed. Peter Fischer was helping with the experiments that Ahmad performed. The Swiss SNF was giving some funding, and the reference is down here. So thank you very much for your kind attention, and happy to take questions if there's still time.
Maybe we have time for a quick question. Thanks, Patrick, for the talk. Anyone for a very quick one? Yeah, Ed, go ahead.
Yeah. So really interesting with the sort of mechanism for actually controlling or applying a kind of strain rate to the surface. But one question I had with the kind of concentrations, are you anywhere near experimental concentrations, or do you have to do what you normally do in molecular systems and make them orders of magnitude larger than kind of real concentrations?
The concentrations of these pluronics, these surfactant molecules.
Yeah, so your gamma basically is that kind of comparable or orders of magnitude larger than experiments?
No, this is we can have a full range of that. That is not an issue there. That's the advantage of these polymeric solutions kind of thing, but because you can vary them a lot, that's fine. I mean, the problem would be if you want to go to very dense interfaces, because then you get a solution limit, and then the rest will be dispersed somewhere in the bulk, and you don't know the effective surface concentration really sitting there compared to the other. But if you stay below that, that's fine. And this was one of the reasons of choosing these ones, because they give quite a strong signal. So there are a lot of surface active polymers where you hardly see any stress response. And so with the help of Peter Fischer and colleagues, we knew kind of which polymers to choose so that we can have a decent range for comparison. But yeah, it's not obvious for all kinds of systems you're looking at. Absolutely.
Great. So thanks, Patrick, for that nice talk. Let's in aspect of time, let's move on to the next talk. So next up we have Professor Suman Chakraborty from IIT Kharagpur, and he'll be talking to us about evaporation of saline aqueous nanodroplets.
We hope.
So Suman, are you here? I thought I saw him.
Suman is here.
Maybe muted or?
I cannot see him in the chat, in the participants list.
I mean, he emailed us 20 minutes ago.
I saw him come in as well, come into the...
Yeah, maybe he's got an internet problem. Is Paola here? Out of interest, the next speaker after.
Hi, yes, I'm here.
Hi, Paola.
Hi, would you mind maybe doing this one? If we don't, might be most sensible, is that?
Yeah, sure.
Give him maybe a couple more minutes and then. Just I'm aware today's quite packed, and I don't want people to have time for lunch, just because obviously if people are still at home, they're going to have to.
Can you see my screen?
Yes, perfect.
Yes, great. Okay, so thank you very much. So my talk is slightly different, I guess, than the previous ones. I will focus more on the thermodynamics of the interface rather than the non-equilibrium properties. But we are in, I mean, once you characterize the thermodynamics, the idea is to go indeed to look at more non-equilibrium properties. So what I'm going to show you is a bit about some work we have been doing in the last couple of years about trying to model this interface. So graphene has been already mentioned in previous talks, so no need to introduce it too much. But basically, is a one-atom thick layer of graphite. It has a very high resonant structure, so formed by carbon, and therefore it is characterized by a delocalized electron cloud at the top and the bottom of the sheet, with all these pi electrons into it. So it's a very flexible and mobile electron cloud. So graphene and as well as graphite are very hard to functionalize. They are not very reactive. However, if you use very potent oxidizing elements, you can actually oxidize both the surface, usually with hydroxylic group, and also the edges where you have the hydrogens that are more reactive, and these usually are replaced with the carboxylic groups. But so when you do this, you obtain what is called graphene oxide. We have been working a bit on graphene oxide, but this talk I'm going to focus only on graphene, so completely unfunctionalized surface. So despite the surface to be, as I was saying, very so not reactive at all, some interesting things happen at the interface between graphene and graphite and electrolyte. So basically, anything can stick to the surface due to this electron cloud formed by these pi electrons that are on the top of the surface of graphene and graphite. And this has been seen experimentally as well as from ab initio molecular dynamics. So we are interested in the interface between graphene and electrolytes. This is because so graphene oxide and also graphene can be used for desalination purposes, for example, but it's also this interface is very much present also in a lot of electronic devices. Experiments, this is a cartoon describing STM experiments, for example, with HOPG, which is this highly ordered pyrolyc graphitic surface, and this should be the ions, basically, of the electrolyte. These are experiments instead with spectroscopic measurements. They both show that there is absorption of ions on the surface of graphene, even when it is is very mildly charged. And this ab initio molecular dynamic simulation performed on carbon nanotubes with, again, an electrolyte that has been flown through, pushed through it. And again, this ab initio NEMD showed that there is absorption of ions. And the main reason is because this is known actually in organic chemistry. There is this interaction, call it the pi-cation interaction. So the cations absorb on the surface and they polarize the surface because of this distribution, very high mobile pi electrons that are on top. The problem, if you want to model system larger than the ab initio molecular dynamics allow you to do, and you use a standard molecular dynamics, of course, this polarization effects, that is the reason as why ions are driven to the surface, is totally lost, because you use this fixed distribution of charges that don't allow to see polarization. So you have to use polarization force field, for example, or other procedure to look at this polarization. So, for example, if you perform simulation with the standard force field and you look at of graphene with an electrolyte, this was again sodium chloride, I think. What you see is that if you look at the distribution of the ions as a function of the distance from the graphene, you see this depletion region. So ions are actually repelled from the surface and it tends to stay well hydrated in the bulk. So you can use polarizable force field, and I actually developed together with Alessio, who is one of the speakers this afternoon, a very nice one for some organic molecules. But the problem with, as I'm going to show you later, this polarizable force field allows polarization, a very localized polarization, usually related to a bond, so where you have a distribution of electrons through the bond. But this electron cloud instead is very much distributed across the entire surface, so you need a different approach. So experimentally, I was saying you can see absorption of ions on the surface, but the experimental data are very confusing. I mean, you can really find a lot of different results. So for example, this is an example of electrochemical measurements. This is the specific capacitance, which is a value that is directly related to the amount of ions you absorb on the surface. And this experiment has been performed on these highly ordered pyrolytic graphitic surfaces, so very atomic smooth surfaces, but it's still graphite, so several layers. And these experiments, again, this is again the specific capacitance measured on, I think it was a bilayer of graphene actually. So you can see that here what it looks like is that the specific capacitance, the value of the specific capacitance depends on the ion. So there is an ion-specific behavior. So some ions are more absorbed than others, but exactly the same experiments seems to show instead the opposite, so that there is no ion specificity. And there are many other results in the literature on carbon nanotubes as well, activated carbon and generic carbon electrodes. And then there are different explanations to justify ion specificity and no ion specificity. In this case, the explanation is that basically the water polarizes the surface and covers any ion effects. In this case, instead, there is a relationship between the size of the ions, that was the explanation given in this paper, with the relative, so with the capacitance, so with the absorption. So we did some calculations ourselves because we were very interested to see what happens and why these ions are absorbed or not. And we initially started with DFT calculations. So if you perform DFT calculation of, for example, a flake of graphene with an ion on top of the graphene, and then you calculate the absorption energy as the difference in energy between when the ion is far away from the surface and when it's absorbed, you obtain negative absorption energy, meaning that the ions are absorbed, but these are very huge numbers. You have the trend that you expect, so smaller ions absorb, the larger ions absorb the most, and divalent absorb more than monolayer. Divalent absorb more than monovalent ions. However, if you take into account that the ions are very happy in the bulk, and so because they are hydrated there, and then you perform the FT calculation rather than in vacuum with an implicit solvent, then you see that the absorption energy are still negative, so there is still absorption. values are much smaller, and also there is no specific trend with the ions really. So what we want is to perform molecular dynamics. So one idea we had was to basically take this value of absorption energy that we calculated with an implicit solvent DFT calculations and optimize the epsilon value of the Lennard-Jones potential between the carbon and the ion until we were not reaching the same minimum in the absorption free energy that we obtained from the DFT. This is because in the DFT, when you use an implicit solvent, the absorption energy you calculate is actually free energy, not just an energy. So what we basically did was we had a flake, the same size as the DFT, the same size as the one we use in the DFT calculation. We put an ion in the water, explicit water in the molecular dynamics, and we slowly pull the ions towards the surface of the graphene. And then we kept on changing the value of the epsilon between the carbon and the ions until the minimum in the potential of mean force, which is this thing here, was matching the value that we were obtaining from the DFT calculation. So, for example, this is the potential of mean force obtained with the original force field, which was an OPLS, where basically there is no polarization effect, and indeed there is a repulsion of the ions because the PMF is positive, and the solid line corresponds to the PMF with the modified version of the epsilon, where we basically optimize just this value here, down here. We don't know what happens in the middle here. Okay, so the idea was that in this way we had a very simple Lennard-Jones potential that can describe this polarizability effect. And then we run just molecular dynamic simulation for various ions at different concentration, etc. And then what we saw is that the ions absorbed as we forced them to do, basically. But it was quite interesting because we realized that basically the arrangement of the water in the first solvation shell, because for the ions, in order to absorb, it has to dehydrate. So the fact that the ions were absorbing or not was also related not only to the hydration free energy, the size of the ions, but also the way the water were rearranged in the first solvation shell. So for example, potassium absorbed, but in order to absorb, it has to lose a lot of water molecule in the first and second solvation shell. But magnesium, for example, tend to absorb anyway. It needs to, in order to absorb, needs to lose some water molecule in the first solvation shell, but no water molecule in the second solvation shell. So there was a very complicated balance between size, hydration free energy, and the distribution of the ion of the water in the first and second solvation shell. There was, however, a limitation in this approach. The first one was that in the parameterization of the Lennard-Jones, we use only one ion. So we totally lost the effect of the ion screening, so the presence of other ions into at the surface, basically. And this was taken into account through the Lorentz-Berthelot rules. We also parameterized this epsilon, assuming that interaction between the carbon and the ions could still be modeled with the Lennard-Jones 612 and not other, for example, form of Lennard-Jones. Also, the DFT calculation using a continuum implicit solvent model. So this basically underestimate the dehydration free energy cost because you can basically use just fraction of water molecules. So the ion can still feel kind of being hydrated even when it's very close to the surface because it can be hydrated by fraction of water molecule. But in reality, an ion, if dehydrate, lose integer value of water molecules. So there was an underestimation of the dehydration variation cost. So ideally you go for a full QM approach. This has been attempted 2 years ago. Basically, these were calculations done by Zhang in the US, where they did a PM, so an implicit, so a quantum mechanical DFT calculation with an implicit solvent. The difference is that they could take into account concentration of the ions in this implicit solvent. But here again, basically what you lose any dynamics information because basically what you do is take an ion and you force in different positions away from the surface with an electrolyte around. So what we wanted was still to run molecular dynamics. So we came up with then this workflow where we couple quantum mechanics and classical molecular dynamics simulation to model the interface, also because we wanted to model both neutral and electrified interfaces. So basically the approach is very simple. What we do is that we have a simulation box that looks like this. For example, all these little points is the electrolyte, so the water atoms and the ions. And then in this specific case, we have a flake of graphene. We start the simulation with a random distribution of partial charges on the graphene sheet. Then after a certain number of n number of time step in the molecular dynamics, what we do is that we take the configuration of the electrolyte and the position of the carbon atoms of the graphene, and we perform a quantum mechanical calculation where we have this additional Coulomb potential in the DFT calculation that is created by the relative position of the electrolyte with respect to the position of the carbon of the graphene. So in this, then through this DFT calculation, which is actually a DFTB calculation, we can recalculate the partial charges on the carbon, and these partial charges correspond to the partial charges due to the relative position nearby the carbon of the electrolyte. Then we perform another molecular dynamic simulation for a certain number of steps, and then we extract again the configuration, we do the DFT, and we recalculate the partial charges on the carbon, and so on and so forth. So the procedure looks a bit maybe cumbersome, but it's quite quick at the end because we perform DFT-B calculation. So at the moment, I think we actually now can go even faster than that. So very large system, and we have at the end the full electronic structure of the graphene, and we can apply an electric field, so we can actually charge it, etc. So that's, I'm going to show you with the results on that. I just also want to show that now we actually have a new workflow that is even faster, because we have been able to replace completely the DFT-B calculations, the quantum mechanical calculation, with the neural network that has been fed with the DFT-B calculation. So now basically the procedure is even faster than that. So it's basically as fast as a standard molecular dynamics. So we basically, with this procedure, we can actually see the proper polarization of the graphene. So for example, let's say I have this flake of graphene. I have an ion that is a different distance from the surface. So I see the surface from the top in this case. So the ions is at different distances from the surface. And I can calculate how much is, so for example, here what we plot is just the total charge of the carbon in the first ring, in the second ring, in the third ring, etc. So, okay, zero is just because zero is nothing. Okay, so basically the whole thing the plot start here. So the various colors correspond to the distance of the ions from the flake of the graphene. You can see is that as the ion get closer, so from the blue, red, the blue, the green, the red, and the black curve corresponds to ion approaching the surface. The amount of charge that is delocalized, so that actually it's created by the presence of the ions increases. And you can see is that I was mentioning before, this polarization is very, very large in size, because basically the effect of the ions is felt up to here. Then with the procedure, we can actually run simulation for large systems with different concentration of the ions. So we focus on this initially with this sodium chloride electrolyte. And so we calculated, so this is the density profile of the ions. So here this is where the graphene is. And basically it's a mirror. So we have a graphene and then we have a reservoir of electrolyte on both sides. And these are results for uncharged graphene. And we look at basically if the ions are on the surface or not, and what is the effect of the concentration of the electrolyte. So what we saw is that basically, because here there's the graphene, what actually is in direct contact with the graphene is always water. The ions do not dehydrate completely. So sodium is the one that is closest to the surface of the graphene. The anion, as we expected, is much further away, but the amount of ions that are totally dehydrated is very tiny. It was also interesting that if you increase the concentration of the electrolyte, you can see that the cations, so the sodium, actually, so the peak decreases, so there is less cation in the proximity of the surface if you have a higher concentration of the electrolyte than less, and this we think is due to probably ion correlation effect. So we didn't expect, to be honest, these results. We thought that the sodium was actually gonna to dehydrate, so we tried to figure it out what's going on. And then what you can do is we just calculate the energy of these ions as it was approached. So we basically have a fixed ion that approaches the surface at different distances, and then we have an electrolyte nearby, and then we calculate how much is the energy between the ion and the carbon, so the surface of the graphene, as the ion approach. So, and we separate the Coulomb term to the Lennard-Jones term. So, and we look at this at different concentration again. So when the ions is far away, of course, it doesn't feel the graphene at all. And then it starts to be actually attracted from the Coulomb, from the electrostatic interaction when it's roughly at 3 angstrom. But what happens is that in the case of chloride, which is much larger, there is the Lennard-Jones energy that as soon as, from the electrostatic point of view, the ion is absorbed, so it tends to absorb, and there is a negative energy, a Coulomb energy, due to polarization. The Lennard-Jones shoots up, so the chloride will never really dehydrate. The sodium, however, should, because you can see that the Lennard-Jones is always negative. So overall, the absorption energy is negative, but the ions doesn't dehydrate. And the reason is because sodium has a very high solvation-free energy. So in order to dehydrate, even for 1 molecule of water, there is the need of a very strong absorption energy. So a full dehydration probably is not going to happen with neutral graphene. Then what we did, we charged the surface. We charge with a voltage, a negative and a positive voltage. And we expected ions this time to dehydrate, but instead what we found, so if you look at what happens when you negatively charge the graphene, we expected sodium to dehydrate and enter into the Helmholtz layer, but instead it doesn't. What it does is that there is a higher concentration of sodium near the surface compared to when it's uncharged, but it doesn't dehydrate. Chloride, as you expect, moves much further away from the surface. When the surface is positively charged, chloride still stays quite far, and as you expect, the cation is repelled. So basically the result here is that sodium doesn't dehydrate and absorb it with a total dehydration. However, it's still within a very small distance from the surface. So it is probably within the Helmholtz layer, but it doesn't dehydrate. Then, because we have the full quantum mechanics of the graphene, what we could look was also at what happens to the electrostatic potential. So we could actually see if graphene change is properties, electronic properties, basically. So one point was to see if graphene changed from a semi-metal to a metal behavior when ions approach the surface. This was suggested from some DFT calculation. So what we did, we calculated the electrostatic potential on the graphene atoms, so the electrode atoms, when the graphene is negatively and positively charged. So if the graphene is a metal, what we should see is that basically all the atoms have basically the same electrostatic